Good morning, students. So in this session we will discuss about the endpoint. So n is equal to, will take endpoint n will take n is equal to 4 and n is equal to 8, both will take FFT algorithm. So the FFT algorithm, in the FFT algorithm, decimation in time, decimation in frequency, radix to FFT, and both radix to FFT algorithm. So before solving some of the problems, so last session we have discussed about the what are the difficulties of DFT. Okay, so the DFT equation, so x of k, which is equal to, what's the DFT equation? So the summation of k is equal to, that is n is equal to 0 to n minus 1 x of n into, so w power n k. So the w plays a vital role, that is a total factor. So w is equal to e power minus j 2 pi by n into k. So w power k is equal to e power minus j 2 pi by n into k. So the total factor plays a vital role in the computation of FFT. So last class we discussed about the important properties of the total factor. One is the periodicity property, the other one is a symmetry property, because the w power k n, it possesses a circular symmetry. Okay, so because of the symmetry property, how the sequence, the input sequence as divided into even and odd, and the how the even part 0 to n by 2 minus 1, and the other second part again 0 to n by 2 minus 1, even and odd sequence, and again the even part will be decomposed into even and odd sequence, and the odd part will be decomposed into even and odd sequence. So because the w per kn possesses circular symmetry, so periodically with the period n. So the direct computations DFT requires for endpoint DFT n squared complex multiplications and n into n minus 1 complex additions are required. To reduce the computation, the FFT is developed, in which the base radix, the relationship between the base and n are related by n is equal to r power m. So it may be a radix 2 or radix 4 algorithm, and the endpoint computation, so the 50% of the computations reduced compared to DFT algorithm because of this total factor. So the redundant computations are eliminated. So how the endpoint, okay, the endpoint n is equal to 8, for example, n is equal to 8, endpoint DFT. So the k value varies from 0 to n by 2 minus 1, so which is equal to 0 to, for example, 8 by 2, 4 minus 1, 3, 0 to 3. Okay. So no need to discuss again about the periodicity property and symmetry property. So that is the symmetry property is W power k plus n by 2, which is equal to minus W n k. So this also plays a vital role. This is symmetry property. And then the periodicity property will be W power n k plus n is equal to W n k. So this is also periodicity property. So because of these properties, the number of computations are reduced for calculating the DFT values. Now we will see the structure of decimation in time FFT algorithm, and also in the basic computation we have seen the endpoint is decomposed into, this is n by 2 into n by 2, again this is decomposed into n by 4, n by 4, this is n by 4 and n by 4. So this is 8 point divided into 4 point, again which is divided into 2 point. Okay. So the decomposition will be continued, okay, until you will get a 2-point basic 2-point DFT computation. So the basic 2-point computation can be represented by the two complex numbers AB, the total factors Wn. So these two complex numbers will produce the two complex numbers is equal to A is equal to A plus Wn into B, and this B is equal to A minus this total factors. So the lower being always minus, okay, the total factors with the odd function A minus Wn B. So it will produce the complex multiplication, one complex multiplication and the two complex additions, okay, and the results will be stored in the same place. So the number of storage registers are, so it requires n storage systems, okay, for n point. So the two computations, it requires how many stages are required, because this butterfly operations on two complex numbers A comma B will produce the complex number A comma B, okay. So the result will be stored in the same locations. So totally 2n stage registers are used throughout the computation of the endpoint DFT. So the computations are done in place computation. So the 2 marks question, what do you mean by in place computation? Once the butterfly operation is performed on a pair of complex numbers A and B to produce A comma B, there is no need of to save the input pair A B. So we can store the result of A and B in the same locations. So only 2n stage registers are used throughout the computation of the endpoint DFT. So we can say that the computation are done in place computation. Okay. So with respect to the butterfly, so the number of stages, so the number of stages is equal to m is equal to log n to the base 2. So n is equal to 8 means, so m is equal to 3 stages as required, and each stage per stage n by 2 butterflies, the computation n by 2 butterflies are required. So n is equal to 8 means 8 by 2, 4 butterflies per stage. Okay. So the total number of complex multiplications will be n by 2 log n to the base 2, and this is the total number of complex multiplication. The total number of complex additions will be n log n to the base 2. So all these fundamentals already in detail we have discussed in the last video, last session. So what are the difficulties of DFT, and how the effort is developed, how it is decimated with respect to the time factor n, and with respect to the frequency factor k, how it's decimated, and how the total factor plays a vital role, and how the redundant factors are eliminated, and how it, so that it is saved 50% of the computation compared to DFT computation. 50% is saved, and for endpoint computation, how many stages are required, how in each stage how many 2-point computations are required, and how the sequence length x of n is divided into even sequence and odd sequence, and again the even sequence divided into even and odd sequence again divided into even and odd. So the complete derivation we have seen. So and also the x of n, the sequence, how the sequences are derived. So x of n is equal to x of 0, x of 1, x of 2, x of 3, x of 4, x of 5, x of 6, x of 7. So n is equal to 8-point sequence. The data may be 1, 2, 3, 4, 4, 3, 2, 1, for example. Okay. So this sequence, first as per the derivation, the n samples is given to even and odd function. So x of 0 and x of 2 with respect to the position, x of 4 and x of 6. Okay. Then the even odd functions are x of 1, x of 3, x of 5, x of 7. Again this is divided into, first we will write this one, the inputs given sample, x of 0, x of 1, x of 2, x of 3, x of 4, x of 5, x of 6, x of 7. So here this is a decimation in time algorithm. Okay. Then again it is divided into odd and even, x of 0, x of okay, x of 4 and x of 2 and x of 6 with respect to the position. This is zeroth position, first position, second, third, again even and odd we are splitted. So all the concepts we have already seen. So now directly we will go to the butterfly structure of 8 pointer and how to compute the sequence we will see. So again this will be divided into x of 1 and x of 5 and x of 3 and x of 7. If you see here, this sequence will be binary representation 0 0 0 0 1 0 1 0 0 1 1 and 1 0 0 1 0 1 1 1 0 triple 1. Okay, it's x of 0 binary representation. So what is this? 0 this one, right? 0 0 4 1 double 0 0 1 0 6 the equivalent binary value 1 1 0 0 0 1 1 0 1 0 1 1 triple 1. See, so 0 0 this is 0 0 and 0 0 1. So this is binary representation B0 B1 B2. Okay, so how it is here. So 0 1, so this is reverse 0 0 and 0 0 1 now 1 0 0. Okay, bit reverse. This is a natural order. This is a natural order. This is called natural order. So here x of 1, this will be 1 double 0. So this direction bit reversal order. This is called bit reversal order. Okay, x of 4. Then this is 0 1 0 0 1 0 and 0 1 1 1 1 0 0 1 1 1 1 0 1 double 0. So 0 0 1 and 1 0 1 1 0 1 1 1 0 will be 0 0 0 1 1 triple 1 will be. So this is a bit reversal order. Okay, so in decimation in time radix 2 FFT algorithm, the inputs are bit reversal order. Okay, the x of n should be in the bit reversal order. Okay, so these two, one butterfly, these two one computation. Okay, these two will be one computation and these two will be one computation and these two will be one computation and these two will be one 2-point butterfly computation. So we have seen the 2-point butterfly computation we have to perform this 2-point per butterfly computation. For example, this will be x of 0 and first butterfly x of 4. Okay, so what is the 12th factor we will discuss now. X of n should be bit reversal order. Outputs are in natural order. That is x of 0, x of 1, x of 2. Okay, now we will draw the structure for 8 point. Before that, the total factors, so n is equal to w per k, which is equal to e power minus j 2 pi by n into k. N is equal to 8. So k is equal to 0 to n by 2 minus 1. So k equal to 0 to 3. So when k equal to 0, w per 0 is equal to this will be 1. Okay, this will be 1. W0 is 1. Similarly, for k equal to 1, W power 1, that is nk. This is equal to n is 8. Okay, n is equal to 8. For example, n is equal to 8. We can write e power. So n is equal to 8 means first you reduce the equation. Wnk is equal to e power minus j 2 pi by n is 8 into k. So w per k n is equal to e power minus j pi by 4 into k. So k equal to 0. So w1 is equal to w is equal to k equal to 1. So e power minus j pi by 4 into 1 into 1. So you can write which is equal to cos pi by 4 minus j sin pi by 4. This is equal to 1 by root 2 minus j 1 by root 2. So you can write 0.707 minus j 0.707. Okay, similarly, what is k is equal to 2, w2 is equal to e power minus j pi by 4 into k value is 2, no? So we will e power minus j pi by 2, e power minus j pi by 2. You can write cos pi by 2 minus j sin pi by 2. So in that case, correct, w2 equal to minus j. So you will get minus j. W2 8. So W1 is, this is W1 8. W1 8. W2 8. Similarly, W3 k equal to 3. So W3 8 is equal to e power minus j pi by 4 into 3. So e power minus j 3 pi by 4. So you can write cos 3 pi by 4 minus j sin 3 pi by 4, which is equal to minus 1 by root 2 minus j 1 by root 2. So that you can write minus 0.707 minus j 0.707. So this is W38. Okay. Now with this we will draw the 8-point structure, butterfly structure. Oh, different colors is there. Okay. We'll light gray. Okay, we'll take this color. Okay, so 8 point. Eight lines, 8 points, since n is a 8 point, no, so 8 lines you can do. 6 or 2, 4, 6. So 3, 6, 7, one more. Okay. Okay. Now the input should be bit reversal order. Okay. So x of I'll write black x of 0, x of 0 and x of 4 and x of 2, x of 6 and x of 1, x of 5, x of 3 and x of 7. Okay. So input should be in the bit reversal order. So the 2-point computation we'll see now how it will be. So first stage I'll use red color. Okay, red color, I'll use the points how to draw. The 2-point butterfly, the basic 2-point computation will draw. So this is the basic 2-point butterfly computation. Okay, this arrow mark should be. So all the butterflies should have, lower wing should have minus, and the total flutter should be with the odd function only. Okay, so this is the 12 factor. So the 12 factor will be, for example, first stage W08. What is W081? Okay, this will be. Similarly here x of 2, so this is another. So each how many stages for this endpoint? N is equal to 3 stages, is it? So 3 stages. So the basic 2-point computation always it will be W08. It is, since it is a 1, no need to vary. Okay. And next one is, this is a 2-point butterfly computation for x of 1 and x of 5. Minus 1, minus 1. Another 2-point butterfly computation for x of 3 and x of 7. Okay, all the lower wings should have minus 1. So this lower wing W08, W08, 08. This the basic 2-point computation for 2 complex numbers x of 0 and x of 4. The basic 2-point computation, it performs it produces 2 complex numbers a and b, that is equal to, the output of this will be x of 0 plus this x of 4 into W08. Okay, so already we discussed on the 2-point computation same in each stage. So in each stage n by 2 butterflies. This stage, what is the n is equal to 8. So n by 2 butterflies, 4 butterflies. This is one butterfly, second butterfly, third butterfly, fourth butterfly. You want, you can extend this also. Okay, we'll extend this one. Okay, now the Again this 2-point computation, this will be combined into 4-point sequence. So this is a 4-point sequence. I will take another color. Green color I'll take. Okay. So 4-point combined into 4-point. So this is stage 1. You can try, this is stage 1. This is stage 1. This is second stage of computation. So in this computation, it is combined into 4-point, the 4-point sequence. So the first butterfly, see, this is the first butterfly. Okay, first butterfly, the first butterfly. Okay, this is the first butterfly. The second butterfly, we will take another color, pink. I'll take pink color. So the second butterfly, this is second butterfly. Okay. So this butterfly lower wing should have -1. For the butterfly lower wing should have -1. So the lower wing, so this butterfly lower wing only, so this butterfly lower, for this butterfly lower wing only 12 factors will be. So this is the multiply, the output is x of 2, x of 6. This is multiplied by now the 12 factor W08. Similarly, this butterfly, this lower wing should multiplied by W0, W28. Okay. So same structure you can draw the second butterfly. This is second butterfly. This butterfly, so this lower wing. Okay, the other next butterfly, X. This is the second butterfly. Okay, so the lower wing should have -1, and this lower W08. Similarly, this lower wing will be W28. So this is -1. So this is second stage, stage 2 structure. In each stage n by 2 butterflies you check. This is 1 2 3 4. Here also 1 2 3 4 butterflies. In each butterfly the lower wing should have the total factors. In the second stage W08, W28, W08, W28. Okay. Another one. Okay. Okay, third stage diagram will take. Third stage blue color will take. This is third stage, 8 point. 4 points are combined and these are the 8 points. Just to draw neatly, you can take like this. So the first butterfly, so blue color, this is the first butterfly. So the first butterfly will draw. Okay, so this is the first butterfly. This is the first butterfly. Okay. Similarly, the second butterfly will take orange color. Will take orange color. This is the second butterfly. This second butterfly. Second butterfly. Second butterfly. Okay. This is third butterfly. Green. I'll take this color. Okay, pink, pink, pink. This color I'll take. Pink. Okay, we'll take different colors. This color. So these are the next. Next butterfly. I will take pink. Okay. This is the first. So all the lower wings should have -1. This butterfly should have -1. This butterfly should have -1. This butterfly lower wing -1. This butterfly lower wing -1. So all this butterfly. So this lower wing should have W18. W18. Second one, this butterfly W28, and the third one, this butterfly W08. This is W08. This is W18. 1. W28 purple. This is W38. Okay. So now the output of this will be, which color I can choose? Rainbow color. How it will be? X of 0, X of 1, X of 2, X of 3, X of 4, X of 5, X of 6, X of 7. Okay, this is a n is equal to, this is n is equal to 8 point decimation. This is stage 3. Stage 3. In stage 3 also, how many butterflies? 1, 2, 3, 4 butterflies. N by 2 butterflies. Here also in stage 2 also, n by 2. 4 butterflies. 1, 2, 3, 4 butterflies. N by 2 butterflies. Here also in the stage 1 also, n by 2 butterflies. Okay. This is the structure of 8-point decimation in time reduced to FFT algorithm. Okay. So you can take some example for n is equal to 8-point DFT. Similarly, you can draw the decimation time for 4-point DFT also. So we will draw the 4-point DFT structure also. This is 4-point DFT structure will draw. Okay. So for 4-point sequence, x of n is equal to x of 0, x of 1, x of 2, x of 3. Okay, it may be 4-point DFT. So the even sequence x of 0, x of 2, x of 1 and x of 3. So this computation will be decimation in time FFT algorithm. So n by 2 butterfly in each stage, 4-point n is equal to 4, 4 by 2, 2 butterflies in each stage computation. Minus 1, so the error should be minus 1. So W 0 4, this is W 0 4. So here the computation you have to perform. W per k is equal to e per minus j 2 pi by n into k, no? So where n is equal to 4, so k equal to 0 to n by 2 minus 1, so 4 by 2, so k equal to 0 to 1. So when k equal to 0, W power 0 4, which is equal to 1. Okay. W04. Similarly, W power k equal to 1, W power 14 is equal to e power minus j 2 pi by n is 4 no into 1. So you will get e power minus j pi by 2 which is equal to cos pi by 2 minus j sin pi by 2. So W14 is equal to minus j, this minus j. So W0 and W4 only. Okay. The second, this is a first stage 1. This is a stage 1. How many stages? So n by 2 stages. 2 stages will be there. Then we'll take another color, green color I'll take. Okay. So the second stage will be for this will be 4 points. We'll take blue color. So lower wing should have -1. The second butterfly will take this one. Second butterfly. Then pink color, we have to choose pink color, no? Okay, pink color. Okay, so the lower wing should have -1. All butterflies lower wing should have -1. So this total factor the other, this is W14 and this total factor should have W04, W04, W14. Then the output will be x of 0, x of 1, x of 2, x of 3. The input should be a bit reversal order. The output should be a natural order. Okay, so can draw neatly. Okay, so this is a 4 point, this is stage 2. This is stage 2. 4 point. So this is a decimation in time algorithm. 4 point. This is 4 point decimation in time FFT algorithm. Okay, so this is the structure. Similarly, you can draw the, so the lower wings, remember that here only W04, here W04 and W14 is to remember the structures. Similarly, decimation frequency FFT. If we draw the structure of decimation frequency FFT, the decimation frequency FFT, decimation frequency FFT, okay. I'll give an example. 4-point LDR, then 8-point decimation. So, okay, decimation time algorithm. Okay, I think the decimation frequency in the next section we will discuss. Okay. So, for the given sequence, we will take one problem.